When a ground fault develops in the secondary side of a transformer, a path to ground is created, allowing current to flow through the faulted circuit. The secondary overcurrent protection, such as fuses or circuit breakers, should trip to clear the fault, interrupting the current flow. If the secondary overcurrent protection fails to trip, the fault current will continue to flow, heating and potentially damaging the transformer. A short circuit on the secondary side of a transformer is a direct connection between the live and neutral conductors, resulting in a low impedance path for current flow. The secondary overcurrent protection should trip immediately to clear the short circuit, interrupting the high current. If the secondary overcurrent protection fails to trip, the short circuit current will flow through the transformer to the primary side. Most utility transformers have secondary overcurrent protection using fuses or circuit breakers to protect against faults on the secondary side. This protection is typically located in the transformer enclosure or in a separate distribution panel. If the secondary overcurrent protection fails to clear fault, the short circuit current will flow through the transformer to the primary side. The primary overcurrent device, such as a circuit breaker or fuse, will trip to protect the transformer from damage. The magnitude of the secondary fault current depends on the impedance of the fault loop, including the transformer impedance and the impedance of the faulted circuit. The secondary fault current may not be high enough to open the primary overcurrent device, but it can still cause damage to the secondary winding and other components. Ground faults and short circuits on the secondary side of a utility transformer are cleared by secondary overcurrent protection. If this protection fails, the fault current can flow through the transformer to the primary side, potentially opening the primary overcurrent device. However, the fault current may not always be large enough to accomplish this, especially if the fault is located far from the transformer. To elaborate, it's crucial to understand the concept of impedance in electrical circuits. Impedance is the total opposition to current flow in an alternating current circuit, similar to resistance in a direct current circuit. It's made up of resistance and reactance, where reactance is the opposition to current flow due to inductance and capacitance. The impedance of the fault loop is a key factor in determining the magnitude of the fault current. A lower impedance results in a higher fault current, while a higher impedance results in a lower fault current. The transformer's impedance is determined by its design and construction. Utility transformers are designed with specific impedance values to limit fault currents and protect the transformer from damage. The impedance of the faulted circuit depends on the length and size of the conductors, as well as any other components in the circuit. For example, a long run of small gauge wire will have a higher impedance than a short run of large gauge wire. The overcurrent protection devices, such as fuses and circuit breakers, are designed to trip when the current exceeds a certain threshold. The tripping threshold is determined by the device's rating. Fuses are designed to melt and break the circuit when the current exceeds their rating. Circuit breakers are designed to trip open and interrupt the circuit when the current exceeds their rating. The overcurrent protection devices must be properly sized to protect the transformer and the circuit from damage. If the overcurrent protection devices are too small, they will trip unnecessarily, interrupting power to the circuit. If the overcurrent protection devices are too large, they will not trip quickly enough to protect the transformer and the circuit from damage. The coordination of overcurrent protection devices is also important. Coordination ensures that the overcurrent protection device closest to the fault trips first, minimizing the impact on the rest of the system. This is typically achieved by using time current curves, which show the time it takes for an overcurrent protection device to trip at different current levels. The time current curves of the overcurrent protection devices must be coordinated so that the device closest to the fault trips before any other devices. The primary overcurrent device is typically a circuit breaker or fuse located at the substation. The primary overcurrent device is sized to protect the transformer from damage in the event of a fault on the secondary side. If the secondary overcurrent protection fails to clear a fault, the fault current will flow through the transformer to the primary side, causing the primary overcurrent device to trip. The primary overcurrent device must be sized large enough to carry the normal load current of the transformer, but small enough to trip quickly enough to protect the transformer from damage. The location of the fault also affects the magnitude of the fault current. A fault located close to the transformer will result in a higher fault current than a fault located further away from the transformer. This is because the impedance of the fault loop increases as the distance from the transformer increases. In some cases, the fault current may not be high enough to open the primary overcurrent device, especially if the fault is located far from the transformer. In this case, the fault current can still cause damage to the secondary winding and other components of the transformer. The heat generated by the fault current can cause the insulation on the windings to break down, leading to a short circuit within the transformer. The mechanical forces generated by the fault current can also damage the windings and other components of the transformer. To prevent damage to the transformer, it is important to have properly sized and coordinated overcurrent protection devices. It is also important to regularly inspect and maintain the transformer to ensure that it is in good working condition. Regular inspections should include checking the oil level, the condition of the bushings, and the tightness of the connections. Maintenance should include cleaning the transformer, tightening the connections, and replacing any damaged components. Furthermore, consider the role of grounding and fault clearing. A properly grounded system provides a low impedance path for fault current to flow back to the source, which helps to ensure that overcurrent protection devices will trip quickly and clear the fault. There are several types of grounding systems, including solid grounding, resistance grounding, and impedance grounding. Solid grounding provides the lowest impedance path for fault current, but it can also result in high fault currents. Resistance grounding limits the fault current, but it can also slow down the tripping of overcurrent protection devices. Impedance grounding provides a balance between limiting fault current and ensuring that overcurrent protection devices will trip quickly. The choice of grounding system depends on the specific application and the desired level of protection. Ground fault protection is another important aspect of fault clearing. Ground fault protection devices are designed to detect ground faults and trip quickly to clear the fault. Ground fault protection is typically used in applications where there is a high risk of ground faults, such as in industrial plants and commercial buildings. There are several types of ground fault protection devices, including ground fault circuit interrupters, ground fault relays, and ground fault monitors. Ground fault circuit interrupters are typically used in residential applications to protect against electrical shock. Ground fault relays are typically used in industrial and commercial applications to protect equipment from damage. Ground fault monitors are typically used to monitor the ground fault current and provide an alarm if the current exceeds a certain threshold. The installation and maintenance of electrical equipment must comply with relevant electrical codes and standards. These codes and standards provide guidance on the proper selection, installation, and maintenance of electrical equipment to ensure safety and reliability. In the United States, the National Electrical Code, also known as NEC, provides comprehensive guidelines for electrical installations. The NEC is updated every 3 years to reflect changes in technology and best practices. It is essential for electrical professionals to stay up to date on the latest requirements of the NEC. For example, NEC 215.3 covers overcurrent protection for feeders. NEC 230.95 covers ground fault protection of equipment. And NEC 240 addresses overcurrent protection generally. The NEC also provides requirements for grounding and bonding. Grounding is the connection of electrical equipment to the earth. Bonding is the connection of different pieces of electrical equipment together to create a low impedance path for fault current. Proper grounding and bonding are essential for ensuring safety and preventing electrical shock. In addition to the NEC, other relevant codes and standards may apply depending on the specific application and location. These may include state and local electrical codes, as well as industry standards such as those published by the Institute of Electrical and Electronics Engineers, also known as IEE, and the National Fire Protection Association, also known as NFPA. It's also important to remember that different types of transformers exist, each with unique characteristics. For example, autotransformers have a single winding that serves as both the primary and secondary, which can affect fault current behavior. Isolation transformers are designed to isolate the secondary circuit from the primary circuit, which can provide additional protection against electrical shock. Step-up transformers increase the voltage from the primary to the secondary, while step-down transformers decrease the voltage. The type of transformer used will affect the fault current magnitude and the selection of overcurrent protection devices. In addition, the operating conditions of the transformer can affect its performance and reliability. Overloading the transformer can cause it to overheat, which can damage the insulation and lead to a failure. Operating the transformer at high altitudes can reduce its cooling capacity, which can also lead to overheating. Exposure to corrosive environments can damage the transformer's components and reduce its lifespan. Regular monitoring of the transformer's operating conditions can help to identify potential problems before they lead to a failure. This can include monitoring the transformer's temperature, voltage, current, and oil level. It's crucial to consider the impact of harmonics on transformer operation and protection. Harmonics are sinusoidal voltages or currents having frequencies that are integer multiples of the fundamental frequency of the power system. Harmonics can cause a variety of problems, including overheating of transformers, increased losses, and reduced power quality. Transformers supplying nonlinear loads, such as electronic devices and variable frequency drives, are particularly susceptible to harmonic distortion. To mitigate the effects of harmonics, it may be necessary to use harmonic filters or to specify a transformer that is designed to withstand harmonic currents. The selection of overcurrent protection devices should also take into account the presence of harmonics. Some overcurrent protection devices are more sensitive to harmonics than others, and it may be necessary to use a device that is specifically designed for harmonic applications. Furthermore, consider the impact of inrush current on transformer protection. Inrush current is a high-magnitude current that flows when a transformer is first energized. The inrush current can be several times the normal operating current of the transformer and can last for several cycles. The inrush current is caused by the sudden magnetization of the transformer core. Overcurrent protection devices must be able to withstand the inrush current without tripping unnecessarily. This can be achieved by using time delay fuses or circuit breakers that are designed to tolerate inrush currents. The selection of overcurrent protection devices should also take into account the transformer's impedance and the available fault current. The impedance of the transformer limits the magnitude of the fault current. The available fault current is the maximum current that can flow in the event of a fault. The overcurrent protection devices must be able to interrupt the available fault current without being damaged. The coordination of overcurrent protection devices is also important to ensure that the device closest to the fault trips first, minimizing the impact on the rest of the system. Time current curves are used to coordinate overcurrent protection devices. The time current curve shows the time it takes for an overcurrent protection device to trip at different current levels. The time current curves of the overcurrent protection devices must be coordinated so that the device closest to the fault trips before any other devices. Therefore, it is vital to have a comprehensive understanding of transformer protection principles and practices to ensure the safe and reliable operation of electrical power systems. This includes understanding the different types of faults that can occur, the characteristics of overcurrent protection devices, and the importance of coordination. Regular training and education are essential for electrical professionals to stay up to date on the latest technologies and best practices. It is equally important to conduct regular maintenance and testing of transformers and overcurrent protection devices to ensure that they are functioning properly. This includes visual inspections, insulation resistance tests, and functional tests. By following these practices, electrical professionals can help to prevent transformer failures and ensure the safety and reliability of electrical power systems. It is also important to consider the use of advanced protection schemes, such as differential protection for larger or critical transformers. Differential protection compares the current entering and leaving the transformer. If there is a difference in the current, it indicates a fault within the transformer, and the protection system will trip to isolate the transformer from the system. This type of protection is very sensitive and can detect faults that may not be detected by overcurrent protection alone. The application of differential protection requires careful consideration of the transformer's characteristics and the system configuration. It is important to properly set the differential protection relays to avoid nuisance tripping. Another advanced protection scheme is sudden pressure relay protection. This type of protection detects a rapid increase in pressure inside the transformer tank, which can indicate a fault such as an arcing fault. The sudden pressure relay will trip to isolate the transformer from the system. This type of protection is particularly effective for detecting internal faults that may not be detected by other protection schemes. It's also important to consider the environmental conditions in which the transformer is operating. Transformers located in harsh environments, such as coastal areas or industrial plants, may require special protection measures. This can include using corrosion-resistant materials, providing additional insulation, and implementing regular cleaning and maintenance programs. Lightning protection is another important consideration for transformers located in areas that are prone to lightning strikes. Lightning strikes can cause high voltage surges that can damage the transformer insulation and lead to a failure. Lightning arresters are used to protect transformers from lightning strikes by diverting the surge current to ground. The lightning arresters should be properly sized and installed to provide adequate protection. Lastly, the aging of transformers is a significant factor that must be considered. As transformers age, their insulation deteriorates, and their ability to withstand faults decreases. Regular testing and monitoring of the transformer's condition can help to identify potential problems before they lead to a failure. Replacement of aging transformers may be necessary to maintain the reliability of the electrical power system.